is anybody else feeling brave enough to propose another reaction here? Sure. I think what I'll say is slash LAH. Does that seem fair? Yeah. And that's not totally distinct. Also in orange, we could have had an aldehyde to get that starting material. And we could have had an anhydride. Although it's important to remember that only one equivalence of the anhydride would actually get reduced to the alcohol. The other equivalence of the anhydride, whatever's on this other side, would stay a carboxylic acid. In LAH, I could have had a carboxylic acid, because LAH will work for any of these, but LAH will only work for some of these more strong ones. And I could have also had an ester. But much like how the anhydride would get reduced to have a leftover part in NaBH4, the ester would get reduced to have a second alcohol. Maybe I don't want to have two alcohols. But if I ever say propose a synthesis, look at how many correct starting materials there are. It's like an endless array of right answers. Okay. What about on top? Peyton gave us SN2. Are there any variations to that I could have had? Do you need this?
Was it the one you gave last week?
I think so. So actually, SN1 doesn't happen readily on primary carbons. Can anybody tell me why? Why does SN1 not happen readily on primary carbons? Sorry? Unstable carbocation. SN1 has a carbocation intermediate, and typically an SN1 mechanism proceeds because the carbocation is the most stable way for that reaction. In this case, SN1 would not be more stable. It would require more energy than just going through SN2. Hydroxide there is a great answer. But you could have also had a weak nucleophile like water. And typically we say that weak nucleophile might do SN1, but it won't on a primary carbon because it's easier to do SN2 than SN1. So SN2 using hydroxide or water, great. Anti-Markovnikov hydration of an alkene, great. What other ways have we learned how to make alcohols? Could I run an NAS reaction to get this product? Why can I not use SN1? There's no aromatic ring involved, exactly. So NAS doesn't make any sense here. In the same way that SN1 doesn't really make any sense. It physically doesn't apply. Good. Could I use acid catalyzed hydration or oxymercuration reduction? No. Because this starting material is actually the one that we demonstrated with last week when we did all of the different preparations of alcohols. Acid catalyzed hydration goes through a carbocation intermediate and a carbocation rearrangement. Hydroboration oxidation, nope, sorry, that's what we have. Oxymercuration reduction is Markovnikov addition without the carbocation rearrangement. So really, this alkene can only give me this alcohol by my anti-Zaitsev hydration. Sorry, anti-Markovnikov. My hydroboration oxidation mechanism. What other ways did we learn how to make alcohols? If you've got that sheet, this is a good place to look. I'm trying to remember all the things I even told you. I can't do halohydrin addition because I don't want any halogens on here. I can't do diol addition. You mean like to an aromatic ring? No. Aryl addition?
Did on the board.
For
Those
acyl.
sorry.
Sorry.
Stab you.
Acyl addition.
Well, this one's arrow above it.
No, that's a C.
No, that's an R. How
It,
you
sh-
wrote
it, it should be a C. Sorry. We don't have anything called aryl addition.
Okay.
Acyl addition, exactly. Acyl addition. Someone remind me what the acyl group is. My partner says I get too technical when he watches my videos. What do you think now?
Does he do chemistry?
He does neuroscience.
Oh,
Yeah, organometallics. But what's the acyl group? The carbonyl. What's a carbonyl? CO double bond. Okay, so the last one here that we didn't show would be acyl addition. So I'm going to need a carbonyl group, right? And I'll need an organometallic. It does not matter which one I put as the substrate, the starting material, and which one I put over the arrow. That can be a confusing thing. Typically, the way we decide whether the carbonyl is the substrate and the organometallic is over the arrow, or whether the organometallic is the substrate and the carbonyl is over the arrow, is what we're starting with. Am I preparing something and then adding this acyl addition as a next step? Then I'll show whatever I just prepared over the arrow. If I'm preparing a carbonyl, if I'm preparing an organometallic, that's how I decide. If we're just starting from scratch, it literally doesn't matter, because we could have also just written this as carbonyl and organometallic react, but acyl addition requires a second step. Acyl addition requires acid workup, so it's going to look easiest if we just pick one of them and put it over the arrow so that we can follow it with step 2, aqueous workup. So it doesn't matter where I put my acyl group, where I put my organometallic, but it does matter what the acyl group looks like. In my final product, can you tell me which carbon must have been the carbonyl carbon before the acyl addition? Sarah? Tell me. This one here? Could this be the carbonyl carbon in my starting material? The CO double bond carbon. Why not, Lily?
Well, I just think it has to be that other one, because it's directly attached to that OH group.
Still connected to the oxygen. Whatever carbon is connected to the alcohol, whatever carbon is the alcohol carbon, must have been the carbonyl carbon. So this guy here was a carbonyl carbon. And I did acyl addition. Look, that was also the carbonyl carbon down here. Right? It's that carbon that was already bonded to the oxygen that became the alcohol carbon. So in the same way, when I do acyl addition, that carbon must have been bonded to the carbonyl. So then what carbon was my organometallic? What carbon was my nucleophile? The one that made the carbon-carbon bond to the carbonyl carbon. Carbonyl carbon, carbon-carbon bond, organometallic carbon. You recognize why I'm calling it RM? Why? Organometallic. Okay, so now I can map my carbons. I'm going to count through my nucleophilic attack. That's just how I like to do it. And since I know my organometallic carbon is my nucleophile, I want to have carbon 3 be an organometallic, and carbon 4 will be a carbonyl that gets opened into that primary alcohol. All right, do you have a preference on which you see as the substrate and which you see over the arrow? Okay, then I'm going to show the carbonyl as the substrate, and I'll show the organometallic over the arrow. Here's my carbon chain, 1, 2, 3, and 3 is attached to a metal. I chose magnesium, so I needed to put a halide. I could have put lithium, and I wouldn't need to put a halide. That means that carbon 4 is bonded to nothing. Formaldehyde, or methanal if you use systematic naming. So carbon 3 attacks carbon 4, creates a primary alcohol. That means that the carbonyl carbon before had no bonds to other carbons. Make sense? Here's what I want to show you guys about preparation of carbonyls. Preparation of alcohols. Formaldehyde can do two things. Formaldehyde can form a primary alcohol by reaction with organometallic, and formaldehyde can make methanol by reduction, sodium borohydride or LAH. It's a really useful starting material if I want to make a primary alcohol or make methanol. Any other aldehyde that already has a carbon group attached doesn't make methanol upon reduction, it makes a primary alcohol upon reduction. But with acyl addition, any other aldehyde makes a secondary alcohol. As I increase the number of carbons connected to my carbonyl, I increase the number of carbons connected to my alcohol. So what happens with my ketone? When I reduce it, what type of functional group do I get? Methanol, primary alcohol. Primary alcohol, secondary alcohol. Secondary alcohol. What do I get if I do acyl addition to my ketone? Tertiary alcohol. Do you see that trend? Do you see how analyzing the substitution of your alcohol can actually feed into the substitution of your acyl starting material? Let's analyze this starting question a different way. What type of alcohol have I made? Methyl, primary, secondary, or tertiary? Do you guys agree with Milena? Why? Why is it a primary alcohol? That carbon is only attached to one other carbon. Primary alcohol. If I do this by reduction, how do I make a primary alcohol by reduction? I start with an aldehyde. An aldehyde connected to something else, not formaldehyde. Start with a regular aldehyde. How do I make a primary aldehyde by acyl addition? Acyl addition, primary alcohol needs formaldehyde as a starting material. Changing the degree of substitution at your carbonyl carbon changes what type of reaction you want to use to get a different type of product. Yeah? I want you to pay attention to that change. Pay attention to the substitution. It feeds into what type of reaction you can use. Okay, and why don't we have a quaternary alcohol? I've got methyl alcohol, primary, secondary, tertiary.
Alcohol's four carbons is a quaternary carbon.
Good. Quaternary carbon is already bonded to four things. It can't also be bonded to another alcohol. And why is it I don't have a reduction step that leads to a tertiary alcohol? Look at how my acyl addition matched up with the higher degree of substitution reduction. Acyl addition matched up with higher degree of substitution reduction. Acyl addition, where's my higher degree of substitution? It would actually come back to, if I wanted to do a reduction and I wanted to reduce it to have 3 carbon bonds, what's wrong with that? It's got 5 bonds again. So for the same reason I can't have any sort of quaternary alcohol, these two structures should give you the heebie-jeebies. They can't exist. They don't exist. They won't exist. They lose you points on your tests. Deal? All right. We've gone through preparation of alcohols. We even looked at some reactions. We did multi-step synthesis problems at the end, figuring out how to use reduction selectively. Now, I want us to look at reactions with alcohols. There are a lot of reactions. We did some of these, didn't we? Just one. No. These. Yeah. Okay. I thought this looked familiar. We've done a lot of them, right? Do you need one?
No.
5 of them. Okay, rather than filling them in, let's just recap. Halohydrin. What else? Acid. What did I do next? Not halohydrin. Sorry, haloether. I'm just going to look back at your sheet. Thanks. Right. Substitution. We've got SN1 substitution and SN2 substitution. We've got our tosyl halides. We had, well, yeah, I guess I kind of doubled up on that. And we had elimination, H2SO4 to form the alkene. Okay, so there are 2 left that I want to talk about with you guys. And I'm gonna have my learning objectives document on Canvas pulled up while I do this so that I make sure that we're covering everything that's on your learning objectives and nothing that's not. And I'm saying this out loud to remind you that you can also use that learning objectives document to study. When you're going through and trying to prepare what reactions to know, this is a good place to go. Lily?
The exam is a week from this Thursday, right?
A week from, not tomorrow, the day after tomorrow. Yeah. 9 days? Do you know what we have next week, Tuesday?
Review.
A review day. You're welcome.
Thanks, John.
Yeah, you're welcome. Okay, here are the two that I want to add on to this. These were all previously seen. Oof. Those were all review. These next two are new reactions. Have you heard me say that water is just inorganic alcohol? Which is why water and alcohols do a lot of the same reactions. Halohydrin addition with water as a reagent, haloether addition with alcohol. It's like they're doing the same thing. It's just one has an extra H, the other has a carbon group instead. So one reaction we've done with water that we've never done with alcohol is the acid-catalyzed hydration. Why can't I do the acid-catalyzed hydration, but instead of water, have alcohol and acid? And that's exactly what we'll do next. We'll do our alcohol with an alkene, and I'm going to show the same alkene that we've been going through earlier, and acid. Here's what we know about this. In acidic conditions, the alkene acts as a base, and it protonates, forming a carbocation on the more substituted carbon. This has a carbocation intermediate. It doesn't matter that alcohol is present instead of water. The carbocation still forms. That carbocation rearranges, so I end up with the most substituted carbocation when possible. That's what my nucleophile attacks. So instead of getting alcohol, because water is a precursor to alcohol, I now get an ether, because alcohol is a precursor to ether. All right, I'm not going to lie, that's not a very pretty version of the structure, so I'm going to sketch it again and try to make it a little bit prettier to look at. I think that is prettier. Map your carbons. 1, 2, 3, 4. 1, 2, 3, 4. And then if I can map these with primes, I'll call this 1 prime, 2 prime, 3 prime, 4 prime. 1 prime, 2 prime, 3 prime, 4 prime. So what do you name that? We had acid-catalyzed hydration. That was nice because I added H and OH across the bond. I added water. I haven't added water here, so I can't call it acid-catalyzed hydration. It's still acid-catalyzed. So on your learning objectives sheet, I call this acid-catalyzed alcoholysis. It's not a pretty name. So another name that I gave it is acid-catalyzed etherification. I feel like I'm the only one out there trying to name these, though. I'm not seeing other people report meaningful names for these compounds. And to my knowledge, this is also not named after a dead guy. So it's really just, people don't name it. They just say alcohol with alkene and water, or in acid. Do you guys have any preference on that name? Acid-catalyzed etherification?
I have a question. So on that equation, like for example in the structure that has the alkene,
Yeah.
1 prime, 2 prime, 3 prime, 4 prime, those are mapped the way we see them in the product. Like was there a hydride shift going on in there? Or?
There was a hydride shift,
Okay.
absolutely, which means that there's a carbocation intermediate. This structure first becomes protonated to this carbocation, which then rearranges to this carbocation, all in the time before the alcohol can act as a nucleophile. Okay. This term alcoholysis is used when the alcohol is a nucleophile or a reagent. So we say it's a reaction with alcohol, alcoholysis. But esterification, I think, lines up better with the next reaction that I'm going to show you. And that is if I have acid and carboxylic acid. This gives us acid-catalyzed esterification. Okay, so once again, mapping out those carbons, 1, 2, 3, 4. I guess I could have drawn that carbon chain a little different. I just ran out of space. But do you see how a carboxylic acid has now been converted into an ester using an alcohol? This is a mechanism that we will learn later in the semester. Acid-catalyzed esterification. This one was named after a dead guy, and actually 2 dead guys, but only one of them kind of kept the name. This is called the Fischer-Smith esterification reaction, but it's often just called Fischer esterification. How rude to Smith. Also, a lot of things happen, like Beer's law is the Beers-Lambert law, and most people just call it Beer's law. This is what whose ego wins out, you know? This is a time I want to remind you guys that it can be really useful to build a table of reactions where you think about what functional group you're starting with and what functional group you get in the product and what reagents you want to use in between. For example, here, I'm starting with a carboxylic acid, I'm adding an alcohol and acid, and I'm getting an ester. Or am I starting with an alcohol and I'm using a carboxylic acid as a reagent and I'm getting an ester? Right? It's hard to know, huh? Maybe you list it twice. Maybe you think of it one way and recognize that those pieces are interchangeable. Remember earlier I said organometallic, carbonyl, doesn't matter which one is shown over the arrow, which one is shown as the substrate. It's the same deal here. Why did I show the carboxylic acid over the arrow? Because I was starting with my alcohol. I'm talking about how alcohols can react. But my carboxylic acid absolutely could have been here with the alcohol over the arrow. You're still learning how an alcohol reacts. If it helps, take what's written over the arrow and pull it back into Gen Chem terms. A plus B, that's what's reacting. It's just mixing them. All right. There is another class of reactions that alcohols can do, but a quick side note. You'll notice that we said last week that we could do SN1 and SN2 with the alcohol. But do you remember back when we did SN1 and SN2, sometimes we used alcohols if we wanted to promote SN1, a weak nucleophile. But if we wanted to make an ether and we wanted to do SN2, we needed an alkoxide. We needed the conjugate base. Turns out that a dead guy did claim this. And it's called Williamson ether synthesis. We take an alcohol, we react it first with a really strong base. Like a base so strong, the alcohol cannot exist. It is fully deprotonated. I'm using NaH, but I could have also used N-butene, a carbon base that is very strong. And then we introduce an alkyl halide, typically primary or secondary substituted. And we make an ether. Versus what we learned how to do in OChem 1. In OChem 1, we learned how to take an alkoxide and run SN2. The distinction with the Williamson ether synthesis is making the alkoxide. Yeah? This step, ROH with a strong base, gives you the alkoxide. Then you introduce the alkyl halide. Williamson ether synthesis is no different from SN2 other than making the alkoxide, making the strong nucleophile. That's it. All right. Another class of reactions. These are all reactions with alcohols. Williamson ether synthesis, and now oxidation. What was this? Remember that big, you had like 6 different things and they all used the same reagent to make an alcohol? Reduction. Reduction forms alcohols. Oxidation uses alcohols. Reduction decreased the number of bonds to oxygen. Oxidation increases the number of bonds to oxygen. We have 3 major oxidizing agents. First, we'll use chromic acid or hot potassium permanganate. These we consider are strong oxidizers. If I have a secondary alcohol, and I'll be honest, I use chromic acid the most, so that's what I'll put in these examples. Secondary alcohol gets oxidized to a ketone. Basically, the reverse of its reduction. Aldehyde with chromic acid, alcohol, primary alcohol with chromic acid gets oxidized into carboxylic acid. What's my other classes of alcohols? Two other types. I can have methanol. And methanol produces carbon dioxide and water. Bit strange. So I want to show you how that oxidation process happens. From methanol, we do a first oxidation. We remove one bond to hydrogen and increase one bond to oxygen. The first oxidation forms formaldehyde. Chromic acid continues to oxidize then. The second oxidation takes formaldehyde and oxidizes it into formic acid. Again, swaps out a hydrogen for a bond to oxygen. Then chromic acid does a third oxidation. Do you guys know this compound? I know you know it. It's in your blood. Carbonic acid. It's also in your soda, which is why when you crack open your soda, you get all this carbon dioxide released. Carbonic acid decomposes into carbon dioxide and water. So oxidizing methanol with chromic acid with a strong oxidizer might not give you what you want, unless what you're looking for is carbon dioxide, in which case it will give you what you want. I have one other class of alcohol, the tertiary alcohol. What happens to my tertiary alcohol in a strong oxidizer? Nothing. No reaction. Nothing can happen. There's no hydrogen to remove to replace with a bond to oxygen. Okay, I want to ask you guys to solve something quick. Consider how methanol goes through 3 oxidations. All 3 hydrogens are replaced by bonds to oxygens sequentially, one after the other. How many oxidations does my primary alcohol go through to become a carboxylic acid? How many hydrogens are replaced by bonds to oxygen? 2. CH2, OH becomes CO2H. That means that my primary alcohol has a first oxidation followed by a second oxidation. And I don't think I explained this. The O in brackets just means oxidation. Can you predict what that intermediate must be? What do I get when my primary alcohol is oxidized once before it's oxidized into the carboxylic acid? I want you guys to solve it. Take 2 minutes, talk with the people around you, come up with as many answers as you feel comfortable with. What are the possibilities? You want to tell me? Because yeah, I know.
I said, what the hell are you talking about?
Methanol is turned into carbonic acid in 3 steps. Primary alcohol is turned into carboxylic acid in 2 steps. Think about what these intermediates were. Apply that here. I noticed you trying to just go for it.
So you're wanting us to find what reagent we're going to use to get the
Nope. I want to know what the first oxidation intermediate looks like. The alcohol gets oxidized into something that then gets oxidized into the carboxylic acid that we end up with. And if you were to do this in lab, you'd never know. You'd never know that there was an intermediate, but there is mechanistically.
Okay, you just want to know that intermediate.
That's right.
Structure of it.
Think about what I showed with methanol. What's similar and what's different? I liked your guess, Milena, but it.
Yes, I was actually wondering, how should I think about this? Because it's like, if I think about it, either the oxygen is going to become more oxidized or one of the hydrogens is going to be substituted.
Actually, the oxygen, we're not referring to the oxygen when we talk about oxidation, because of course this is organic chemistry. So we're talking about the carbon being oxidized.
Okay.
The oxygen actually will never be oxidized or reduced.
Yeah, okay.
It's the chromium that gets reduced while oxidizing the carbon.
Okay. So in that sense, I should evaluate which of the bonds the carbon has is the one that's most likely to be oxidized.
Yes, I would also consider how methanol gets oxidized. Think about the change in functional groups. With methanol, how would that compare to a primary alcohol?
Okay.
Your idea of looking at which bonds can be oxidized, actually we know it's a hydrogen that will be removed.
Yes.
Comparing it to methanol, I think you can make a prediction about what other bond change is going to happen when that hydrogen gets removed. Okay? Think about the similarity between methanol and a primary alcohol. Think about the difference between methanol and a primary alcohol.
So when it's getting oxidized, the carbonyl is created.
Yes. Doesn't that give you the heebie-jeebies?
Yeah, it's 5. I mean, it's more. 1, 2, 3, 4, 5. Yeah.
Yeah.
So, is this like something breaks?
Where did you get this from?
I'm following your.
On the bottom?
No, I'm following. So I'm looking at how you made methanol,
Yeah.
and I'm seeing the pattern that the carbonyl group is created.
Good.
And so I'm trying to, because I know this isn't right, because that's like what I said earlier.
Yeah.
This doesn't exist.
But also, there's something wrong with this structure. Do you notice how you have all 3 R groups going directly to the O? Rather than all 3 R groups going to a carbon that's bonded to the O?
I wrote down.
Good.
Okay, but then that's
And that's your tertiary alcohol,
okay.
which cannot be oxidized.
No, because that can't.
But if there's a hydrogen at any of these positions,
Okay, that's what I was wondering.
in fact, let me draw that out, Ozzy. Let's go back to the secondary alcohol and notice the change. Carbon hydrogen removed to create a carbonyl. Here, carbon hydrogen removed twice to create a carbonyl. And here, 3 carbon hydrogens removed sequentially. Sure. Not isomers. With our primary alcohol, remove 1 hydrogen, create a carbonyl. Ketone, remove 1 hydrogen, make a carbonyl. Methanol, remove 1 hydrogen, create a carbonyl. After you've created the carbonyl, there are no more carbonyls to make. Remove a hydrogen, replace it with an oxygen. I almost called it an alcohol. It's not an alcohol, it's carboxylic acid. So the secondary alcohol does replace both of its hydrogens, but it actually makes an aldehyde first, and then the aldehyde is oxidized to a carboxylic acid. So if you were to tell me alcohols react with chromic acid to form carboxylic acids, yes, by means of an aldehyde intermediate, which also means aldehydes react with chromic acid to make carboxylic acids. That's a reaction that we're going to look at after the midterm when we get into our carbonyls chapters. But it's going to be a previously seen reaction because you're seeing it now. Ozzy?
I was just wondering if that, no, I think you answered my question.
Okay. Okay, so these were oxidation of alcohols with a strong oxidizer. Let's oxidize alcohols with a mild oxidizer. For this, we'll use PCC. You want to know what PCC is? I bet you'll regret it. No, I said you will regret it. Why is my O so small? PCC stands for pyridinium chlorochromate. Boy, that looks like a relative to chromic acid. You're right. It's a mild version of chromic acid. So what do I mean by mild? Well, when we investigate how the secondary alcohol is oxidized with PCC, we find nothing changes. The secondary alcohol is oxidized to a ketone, the same as with the strong oxidizer. When my primary alcohol is oxidized with PCC, PCC is not strong enough to oxidize the aldehyde that forms. So my mild oxidizing agent produces my aldehyde. I think this should remind you of something. When we learned about hydrogenation of alkynes, we said that palladium reduces an alkyne to an alkene, and then also reduces the alkene to an alkane. But if we add Lindlar's catalyst, this barium carbonate quinoline poison catalyst, the alkyne is reactive and forms an alkene, but now the alkene is inert. It's kind of similar here. With chromic acid, I can oxidize my alcohol to an aldehyde and my aldehyde to a carboxylic acid. But with pyridinium chlorochromate, I oxidize my alcohol to an aldehyde, and now the aldehyde is not reactive enough to continue oxidation.
Is that the same reason, like I think you explained it like surface area?
No, it's the strength of the oxidizer. It's chemically changed. So can you tell me what I can predict to form when methanol is oxidized by PCC? Yeah? Just like how chromic acid forms an aldehyde from methanol and then further oxidizes the aldehyde. Well, PCC can't further oxidize an aldehyde. So after that first oxidation, removal of one CH bond, it's done. Formaldehyde. By the way, this is usually the time in the semester where I like to tell a very sad story. There was a group of college students in Arizona that one student likely worked in a chemistry or biology lab and wanted to bring a gift to an underage party, so they snuck some alcohol out of the lab, brought it to an underage party, spiked the punch, didn't know that there's a chemical difference between ethanol and methanol. They just grabbed the alcohol they found, and dozens, if not hundreds, of underage kids died at that party. Because your body takes in methanol and oxidizes it, pumping you full of formaldehyde, a toxic preserving agent. And if that formaldehyde continues to oxidize, then you have formic acid. Formic acid eats away at everything in your body. So don't drink methanol. In fact, there's an episode of House where medically they followed this accurately. A patient came in with methanol poisoning. They worked in a lab and they were like self-medicating their alcoholism with methanol from lab. Came in with methanol poisoning, and House treated them by giving them shots of tequila. Because to get rid of the methanol in your system, you have to outcompete the oxidation pathway. You have to put something else into your system that won't absolutely kill you by being oxidized. So you oxidize alcohol through the same process. You oxidize ethanol by the same metabolic process that you oxidize methanol, and you can outcompete that oxidation of methanol until the methanol gets flushed. Don't ever drink methanol. Even if it doesn't kill you, it can leave you blind. If you ever find somebody that is overdosed on methanol, you have to get them tequila. It's a very strange process. Okay, oxidation. What happens when I take a tertiary alcohol and I react it with PCC? Nothing. Well, that was a good segue, right? So we have a strong oxidizer, we have a mild oxidizer that actually allows us to do selective oxidation. We also have a radical oxidizer. You might want to think of this, though, as allylic, benzylic. And we'll use manganese dioxide, MnO2. The only alcohols that get oxidized here are alcohols that are allylic and alcohols that are benzylic. And this is a more selective oxidizer. It's not strong, so it will take primary alcohols to aldehyde only. So let's do an example. Ooh, that's kind of a long molecule, huh? But I've got 4 different types of alcohols. Primary benzylic, secondary benzylic, primary not benzylic, secondary not benzylic. So what happens when I react this with manganese dioxide? Anything that is not benzylic is not oxidized. Primary benzylic oxidized into an aldehyde. It's not oxidized further. MnO2 is a mild, selective oxidizing agent.
So the two that did not react, they are not benzylic.
Well, so the MnO2 uses radicals, and the radicals are stabilized by conjugation with an alkene or an aromatic ring. Yeah? So here's another way that I'll pose this. We'll do a specific example. Can you predict the oxidation product for this cyclic alkene diol? While you work on that, take a break. Get up, get your blood flowing, move around. Let's come back at quarter after. We've got one last reaction with alcohols. And then we're going to look at things with ethers and epoxides and do some practice problems. All right?
Can I ask you a question? The one on the very far right at the very top is CH3OH. That's a tertiary? Wait, what is it then? I'm so confused.
Mm-hmm. No, this is a great question.
Because I know that the second one, that one doesn't have a reaction because it's 4, right? Am I just saying? I don't remember how to say it.
So we describe the functional group by the substitution of its carbon,
Yes.
tertiary alcohol. This carbon is bonded to 3 other carbons, tertiary alcohol.
Okay.
2 other carbons,
Oh,
secondary alcohol,
yeah.
primary alcohol.
Okay.
There is no quaternary alcohol because that would be 4 bonds to a carbon plus an alcohol. So we still didn't answer what this is. Is it primary? Is it secondary?
It would be.
Is it tertiary? Is it none of those?
It's none of them because it's not bonded to any other carbons.
Correct. So how do we describe it?
So
It's methyl. That's exactly it. That's the only way to name it. Methyl. Methyl alcohol is its own reagent. It is methanol. Methyl alcohol means a carbon not bonded to anything else, not bonded to any other carbons.
Thank you.
This compound that we've been calling formaldehyde has a systematic name, methanal, because it's just a 1-carbon aldehyde.
Because it wouldn't be methanol.
Yeah. So methanol on the left, methanal on the right. A 1-carbon carbonyl. I typically say that aldehydes are primary functional groups. That carbon is bonded to only 1 other carbon. Carboxylic acids, primary functional groups. But actually formaldehyde is not a primary aldehyde. It's a unique type. It's a methyl aldehyde. Just like we have a primary alcohol, primary aldehyde, methyl alcohol, methyl aldehyde. It's our only way of describing the fact that there's a different number of bonds than you might expect.
Oh my gosh, wait, are you going to,
ACS?
yeah,
I am.
because I saw that you were in the same email as me, and I
You're going for the poster project, or the lab report project, right? Very exciting. We're excited to come see your guys' poster. Have you started making a poster? Good. Okay, who's predicted their product for that reaction? They want me to see it. You get one too? I don't know. One of those is correct, the other is not.
I kind of feel like it underthought.
No. One of those is correct, the other is not. But at the same time, this oxygen having 3 bonds, we'd need to show a positive charge.
Oh, well, that's not meant to happen.
You meant to get rid of the H.
So I'm guessing it's still one wrong, right?
One of them is wrong.
How is it if they're both connected to secondary? They're both secondary? Why are
But MnO2 is not about the substitution. Because in the example above, I have primary and secondary. Right. So can you distinguish that on them? You should do that second one on the bottom. So think of it this way, Indigo. Radical oxidizers, allylic or benzylic.
This would be alloy, right? So this one would stay.
Mm-hmm. Good. Trying that one at the bottom? You're just trying it in your head?
Mm-hmm.
Did you come up with an answer? Oh, it's in a bad spot. Oh, no.
I'm kind of tearing apart watching like what you have on the other thing, and I think where I'm getting a little stumped at is I'm seeing I look at patterns because chemistry really does follow patterns.
Mm-hmm. Absolutely.
And I'm noticing though like these ones it's directly connected to this ring instead of having like a carbon in between
Yes.
benzylic and such. And
Yes.
so I'm trying to notice that pattern with that, but I'm
Now, what do we call an alcohol that is attached just off of the ring rather than more than one carbon off the ring?
I know this answer.
It's on the board. It starts with a B.
Well, it's not. Well, I know the benzylic, but okay. No, that's right. 'Cause
Yeah.
it's off of the ring.
Whatever description we give to the carbon also describes the alcohol. So the carbons connected to the ring are benzylic positions. Now that's a benzylic alcohol.
So both of those would break down to carbonyl groups because I'm noticing the benzylic carbons
Yep.
react.
Yes. And the non-benzylic carbons don't.
Yeah.
But here I don't have a benzene, so I don't have benzylic positions. But I do have an alkene, which means that I have allylic positions.
So your first one that top one would react, and because it's too far away on the other one. However, if we moved it around, which we can't do,
Sure, I mean, chemically we can't do that, but in theory we could draw a different compound, yeah.
like if we, well, I mean, it'd be just pretty much
If it was 1,4,
yeah. Well, I mean, wouldn't that pretty much be the same thing though? Even if you that the alkene, the one, if you just moved that over to like the other spot to make the other one allylic, wouldn't that
True.
pretty much just be the same?
What if we moved the alcohol on the right to be on the bottom? Now both of the alcohols are allylic.
Then both of them could react and
Yeah.
be both that.
Yep.
So the strong oxidizer is capable of adding oxygens in place of hydrogens. Like we say that the strong oxidizers can add oxygens in place of hydrogens.
Yes, the strong oxidizer can substitute hydrogens for oxygens.
And then the mild oxidizer does not, but works with the oxygens already present.
Ooh, brilliant way of saying it. Do you mind if I share that up front? Did you try that bottom one yet? Okay, good.
I don't know.
Can you describe these alcohols?
They're directly attached.
That's what I did.
I said that too.
Sure. Directly attached to a ring. Yeah.
Would
Are
it
they
be-
primary, secondary, tertiary? This carbon,
Is attached to 2?
secondary.
Okay.
This carbon is attached to 2, secondary.
Okay.
This carbon is adjacent to an alkene, allylic. This carbon is attached to a benzene, benzylic. This carbon is not attached to a benzene or an alkene, just secondary, just primary. Primary benzylic, secondary benzylic, secondary allylic.
So this one will change?
Right. Right. Good job, Peyton. Close. Yes. We oxidized too many. Were you telling them that?
Yeah.
Good. Tell them louder. Good. All right. Here's something that Milena pointed out about the difference between strong oxidizers and mild oxidizers. When I took my primary alcohol and I oxidized it with a mild oxidizer, it was able to remove one hydrogen from the carbon, but then it just worked with the oxygen that was already there to make a double bond. But my strong oxidizer can actually remove hydrogens and substitute them for new alcohols, new oxygens. This oxygen is actually the carbonyl oxygen that forms when one of those hydrogens is removed. When that second hydrogen is removed, it's a new oxygen that's added in. Strong oxidizers add additional oxygens, substitute hydrogens for additional oxygens. Mild oxidizers don't. Strong, able to add in extra oxygens. Mild, unable to add in extra oxygens. Okay, down here, I have 2 secondary alcohols. Great. More specifically, I have 1 secondary allylic and 1 secondary. And since MnO2 is an allylic and benzylic oxidizer, my allylic alcohol is oxidized and my non-allylic alcohol is not. Great. Have I told you guys that I learned how to use Reddit over winter break?
Has your world been changed?
I don't know if it's been changed for the better.
What? That's like, literally, I don't need AI because I have Reddit. Like, and I stand by that.
Yeah, subthread chemistry help or chem help. I'm sure I've got like 5 push notifications today from Reddit. Sometimes I respond, sometimes I don't. But it's interesting because I feel like people are posting questions as they come up in class. So I'm watching other classes move through content in real time and like comparing it to how we move through content. It's really interesting.
Until you see one of your questions come up.
I'm waiting for it because I probably could figure out who posted it. Yeah, it's interesting. And every now and then I try to like chime in. It's too much, and I don't get paid for it. I could charge like $30 an hour to get paid to answer people's questions. Instead, I do it for free on Reddit. No thanks. But it's interesting. Anyways, I thought of that because somebody posted a problem where they said their tertiary alcohol got oxidized, and they said, I think my professor is using AI to grade. And I was like, yeah, probably. If he said that was the right answer, it probably was not graded by a chemist. Interesting stuff, though.
Probably TA.
Even a TA would hopefully know that.
We have a lot
I mean, I was a TA once upon a time, and I had to relearn OChem as I TA'd it. I made a lot of mistakes, but that is such a simple mistake. Like, that's day one oxidation. You guys could even tell the difference now. Okay, we've got one last reaction to do here. We've done oxidation of alcohols, but let's do oxidation. I'm going to have you guys fill in the blank here. Oxidation of diols. What type of diol are we looking at? Can you give a name that describes those two alcohols? Okay, yes, 2,3-butane diol. No longer. I need something more vague and less specific. Oh, we're not going to use trans because I could rotate through a conformational change and make it look like they're cis. So it's not that they're trans, but I like that idea. And then I heard vicinal and geminal. Now those are regio terms, which would be good for describing this 2,3 position that Milena had pointed out. But which one is it, geminal or vicinal? How do you know the difference between geminal and vicinal? Yeah, who are my Geminis? It's just me. I'll say it again. Camille, are you a Gemini? I don't know what that means. Okay. But close only counts in horseshoes and hand grenades. Gemini is the twin star sign. So Gemini groups, geminal groups, are attached to the same carbon. Vicinal comes from that word vicinity. But it is not to be mistaken for vinyl. It's not vinyl alcohols, which might also be called enols. Vinyl refers to being attached to an alkene. These are vicinal because they're in the same vicinity, adjacent. Okay. When I react vicinal diols with this specific acid, I get oxidative cleavage to two aldehydes. These can also make ketones depending on the substitution of that carbon. I've only shown one carbon group attached to each alcohol's carbon, but I could have had two R groups, which would leave me with ketones. Who remembers their Gen Chem 1 knowledge and knows the name of that acid? Yeah, periodic acid, which is spelt periodic. I gave this to another student of mine recently. I gave them this name and I said, give me the chemical formula. And they said, I don't know which acid is only periodic. It's good. Okay, that's our last reaction with alcohols. So let's do a short little synthesis and apply a few reactions. Let's start with cyclohexene. Let's take it through 2 steps. And let's get 1,6-hexane dialdehyde. Oh, shoot. Yeah, but I want you to give me 2 steps. Ozonolysis is not a bad reaction. You're right. Ozonolysis could do that in 1 step. I want you to give it to me in 2. Sorry. A reminder for when you're doing synthesis problems, you don't need to have everything filled in perfectly. You can still earn partial credit by having parts of it filled in. Can you figure out what the intermediate is? No?
Sometimes when I'm in their class, like all I can think of is like Dora, because like Boots always asks questions and he's like, "How do you say this?" You know.
Can we do the acid H3O and H2SO4 that add on the alcohol?
No. If I run this with acid catalyzed hydration, I get cyclohexanol, which will not do much with periodic acid. Oh, and I forgot to say, that's the way to emphasize this, per iodic acid, meaning lots of oxygens.
That reaction, like we can see aldehydes there. When does it make ketones?
If there were carbon groups attached here. So if I started with a tertiary alcohol, then I could make ketones.
Could you use like HCl in excess and then from there use the LAH H3O plus?
HCl in excess from this guy, cyclohexene.
Yeah, and then like swap it for. I don't know if that makes sense.
Well, HCl is going to give me chlorocyclohexane. And I could substitute that here for an alcohol, but that it still wouldn't get me any closer to having a vicinal diol. Lily?
Could you do this
Where?
the first step?
Here?
Yeah, because you have to get those oxygens.
I do, yeah.
That's what
But chromic acid won't react with just an alkene. There's something on the way, but chromic acid is not quite the right reagent for us. What do you see? Yes, we can. Cold potassium permanganate. Those of you that have done OCHEM 1 lab here at SLIC, you've done this. You've taken a cyclohexene, although it was 4-methyl cyclohexene, and you've run it with cold potassium permanganate. And by cold, we mean room temp, not boiling. And then what? Now I have a vicinal diol. No. PCC does not do oxidative cleavage. Maybe I should have added this word in, oxidative cleavage. Lily?
The radical oxidizer?
MnO2 won't do anything on here. No reaction. Periodic acid. I've just made a vicinal diol. Now I can cleave the bond between those two alcohols. So HiO4 turns them into aldehydes and breaks the carbon-carbon bond in the same step. That was a little bit more challenging than I had anticipated it being, so I'm glad we did it. Okay, before we move on, at the bottom of that worksheet, under, I've got some stuff about epoxides on there. We've got another couple of practice problems. So, oh, I guess this kind of gave it away though. Can you give me the product that forms when this compound reacts with PCC? And can you give me the reagent needed to give me that compound? That's really too similar to two of the problems I already gave you. Which means it should look familiar and it should make sense. It should be doable. Wait, say what?
I say, right? People have conversations right outside classrooms. Don't they know we're all judging them?
I'm not. Well, just because I can't hear them. What are you pondering, Elliot?
I drew the product before I saw that you said that that product was not.
Mm-hmm.
Yeah, now I'm confused.
I see.
That was.
What, did I draw it wrong? No, you just copied it. We don't know what forms down here.
Yeah, I thought I drew that from PCC.
Oh, I see, I see.
That's the same thing.
Yeah, so it probably is not PCC.
Presumably, unless you're just screwing with it.
Rude. Been known to do it.
This be an allylic?
Close,
Okay.
but not allylic.
It would be the vinylic?
Benzylic.
This is benzoic?
That's right, because it's
Okay.
attached to
The ring?
benzene.
Okay.
Yep, benzylic.
This couldn't be allylic even if this had like the circle in the middle?
We call it aryl.
Okay.
Sorry, these positions, that carbon is an aryl carbon. It's an aromatic carbon, so it's
Okay.
aryl.
Okay.
The positions off of it are benzylic. They're
Okay.
attached to benzene.
Okay. Okay.
It's
thank you.
positions off of alkenes that are considered allylic. It's positions on alkenes that are considered vinylic.
Okay.
So like vinyl, vinylic, attached to an alkene carbon.
Okay.
Allylic, the carbon off of an alkene.
Okay. Thank you.
Mm-hmm. Good, great. Yes. Yes, yeah, good. Great job. Good. And neither is this one.
So I suppose, is this benzoic?
Yeah,
Okay.
yep, it is. No, this is reduction. What you've done here is you've gotten rid of the oxygens and you've reduced those carbons. But this is an oxidizing agent. It should add more bonds to carbon, not less bonds to carbon. PCC takes alcohols and makes carbonyls. Alcohol.
So for this one, why does it remove this oxygen and then double bond it?
Well, it actually does the same thing here. OH, CO becomes C double bond O. CO becomes C double bond O.
Okay.
The orientation is throwing you off. Because the CO bond is now angled, and here the CO bond is coming up.
That does make sense why I got turned around.
Yep.
This is MnO2.
Perfect. Yep. Good. Not quite.
Oh, what the?
That's the same product.
Oh, wait, oh, shit.
Yeah. Might look weird, but it's good. Good. Deep breath. Great. What do you think? What reagent do I need going up?
I have one in my head, but I don't know if I'm.
Yo, how far off was I? Like, did I need to like leave it or anything or no?
No, no cleavage. You just didn't oxidize enough.
So for PCC, it only removes one hydrogen,
Mm-hmm.
right? So would that mean it
Oh, from the carbon.
from the carbon? So would it just remove these? Or is it saying
Per carbon. So this carbon has one hydrogen to remove,
right?
forms a double bond. This carbon has one hydrogen to remove, forms a double bond.
Leave it bonded to OH.
So you're right. It does remove two total. The hydrogen from the O is also removed.
Oh, okay.
But I guess I'm referring there to the carbon. Yep.
I think I just twisted that part in my head. Thank you.
Yep.
Would that be right then?
What you had? Yes. But not with the...
Not with the-
Yeah, you're right.
Okay,
Perfect.
Thank you.
You're welcome. All right, can you do one last one? What happens when this vicinal diol is oxidized with with periodic acid? Both of them turn to what? This? No. They will not become two ketones. Right. What will happen? Two aldehydes. And
Would it couldn't it like break it and then they just become subside, you know?
two aldehydes with no longer a carbon-carbon bond. So here's how I would draw this. I would restart the starting material. That's a good place to start. And now I'm going to break that carbon-carbon bond. Cleave that carbon-carbon bond and make two aldehydes at those positions. That is not the structure that most people would draw. That's not its lowest energy conformation. So it would be easier to think of this as 1, 2, 3, this structure on the bottom, but the structure on top is easier to predict because it resembles the shape of the starting material. Both of them are correct, full points.
The first one going up, it only does one because and then it will stop after that, right?
Right, so this is a benzylic position, and MnO2 is a benzylic allylic oxidizer. So it has no effect on the other alcohol because the other alcohol has no stabilization from the benzene ring. Oof, we're running low on time. So, but the nice thing is, in the fall, I ran out of time in this section. Like, I don't think I even got through all of the last stuff, and we have all of Thursday. We're going to do so much synthesis on Thursday. In fact, you can even take the worksheet that you have, and you can get started on the synthesis problems that are on the back. We'll try to do as many of those as we can on Thursday. So here's what I want to do. I want to look at ethers quickly and review the preparation of ethers. The thing is, we've talked about all of these today already. So I'm not super interested in giving examples again, so I'm just going to highlight them. Haloether addition. Alkene in the presence of a halogen and an alcohol. We make ethers that way. SN1. If I have an alkyl halide and an alcohol, my alcohol will do SN1 to give me an ether. SN2, the Williamson ether synthesis. If I have an alcohol, I can deprotonate it and then do substitution. And then the acid catalyzed esterification. If I have an alkene and an alcohol with acid, I can create an ether in the same way that I would make an alcohol. Same regiochemistry rules apply. The reactions with ethers are not very big. There's not a long list of things. In fact, ethers are pretty unreactive reagents, which is why we use ether as a common solvent in organic chemistry. We use it as a solvent because it doesn't react well to a lot of stuff. The only thing that we can do with ethers is we can put them in the presence of a hydrogen halide acid, hydrochloric acid, hydrobromic acid, and we can run substitution. But it has to boil for a very long time, and it doesn't work very well. Again, the benefit of the ether. It's not going to do this very well. If we run this in an extreme excess, we can actually get the alcohol to then substitute. And that's a reaction we've already seen. Alcohols in HX do SN1 substitution to alkyl halide. And I know I see you guys like, you're Russian. I appreciate it. I don't want to go too fast. This is the only reaction with yeah. Oh, I have a typo on here. I say on my learning objectives sheet that we've seen reactions with ethers in doing SN1, and that's not true. That's what this is, SN1, to reverse the ether. There's a couple of caveats. This is really the only reaction we'll see. A couple of caveats, though. If I have an aryl ether and I try to run this in an excess HX solution, I will never be able to substitute the oxygen from the aromatic carbon. Because the other ethers are going through reaction via SN1 mechanisms. But to do a substitution on an aromatic ring, I would need NAS with a strong nucleophile in basic conditions. I don't have that here. Or I'd need EAS, and EAS will never substitute the CO bond. So it doesn't matter how hard we try, that sp2 carbon never loses the oxygen. Okay. Very rare to see any of those. Oh, did I run out of time?
It's okay, you have 4 minutes before the next professor.
That's not true. Sometimes he's here early. The only other thing that we'll look at on Thursday is epoxides, and then we'll start applying a lot of this into reactions. With epoxides, there's 2 ways to make it. We can take MCPBA and we can make it into an epoxide ring. I'll talk about the next one, the new way to do this, next class. But MCPBA is something that you will recognize better now. MCPBA stands for metachloroperoxybenzoic acid. Now you know what that M is. Meta. So meta. Okay, I don't want to steal any more of your night. We'll look at our second way of forming an epoxide tomorrow. Nope, Thursday. We'll look at the epoxide ring openings that we can do on Thursday, and then we'll do multi-step synthesis, because your homework is multi-step synthesis. In fact, what I would love is for Thursday, we'll do synthesis problems, and I want you to do your homework so that I can grade it Friday, right? If I can grade it Friday, that means I can give you feedback ahead of the unit test this weekend. By the way, unit test this weekend. All right, guys, have a great night. See you all on Thursday.